Uh, Ian needs obviously no introduction, and I'm very excited about this talk. Obviously, something that's a very interesting, intriguing topic. So let's give Ian a round of applause, and over to you, Ian.
Hi everyone, can you hear me? Yes, yes. Cool, so welcome to my talk, Abusing iPhone Co-Processors for Privilege Escalation. So I'm the tech lead of Project Zero at Google. I've been doing Apple tangential security research for, I guess, over a decade now, mostly on the vulnerability research side, so trying to find bugs before other people find them, but more recently, over the last few years, getting more and more involved with in the wild iPhone exploitation and helping on the analysis side. And so today I want to share this story which on the face of it seems kind of run-of-the-mill, but then takes an unexpected twist. And I now realize that the unexpected twist is in the title of the talk. So anyway, imagine this. You're browsing your favorite website on your favorite mobile device. And all of a sudden, the mobile data goes down. You can no longer view your favorite mobile site. And you get a text message, which says something like this. It's time to get connected. To enable data on this device, connect to a Wi-Fi network and head to this link. Then select your device, follow the simple steps, and you'll be good to go. And here's a link. Now, I know what everyone in this room is thinking. Don't click that link. You click the link. And this is what happens. So this protocol here will enable iTunes to go download and install this application. This app is signed with an enterprise certificate, so it will run on your device. And this is what it looks like. But you don't care because you really want to get back on that website. And your mobile data comes back. And you're happy. So it's pretty obvious what's happened here. This is clearly phishing. But there are some really curious aspects to this phishing attack. We know that phishing works best when there's believable context around it. You can be more easily tricked into, in this case, clicking this very suspicious link. And this is a real story that really happened. And we have a copy of this app. We don't know the text message, but this is a real text message that gets sent by this particular network operator. And so there's this curious juxtaposition here of like a fairly run-of-the-mill phishing attack, but to create the context for this phishing attack required quite high-level intervention here, at this case, with the network operator to really disconnect the mobile data of this target. So there's something kind of strange going on here. And this is just one of the curious aspects of this. So we don't have the text message, but what we do have is that app. And so this is inside it. You know, the Vodafone imagery there. It's not a real Vodafone app. And like any good developer, they're linking against a bunch of frameworks. So what's in here? Agent.framework. Fairly suspicious sounding framework to come from Vodafone. Time waste.framework, which means different things to different people in the audience. There is an old iPhone jailbreak that used an exploit called time waste. And there's also an exploit called sock puppet, which sounds a bit like that. And there's an exploit called light speed, like that, and injection kit, and all of this other stuff. So what's going on here? Well, so as I say, 3 of these are just exploits from GitHub. This one is actually GPL licensed in case anyone wants to do some copyright work. This is CVE 2019 from someone on my team, Project Zero. Fixed in 2019, and this is all happening in 2021. So if you were up to date, nothing was going to happen here. This is an even older exploit from 2018. This one is targeting a bug in the Apple video encoder that was discussed at Black Hat EU 2020. And there are 2 more, even more interesting ones, which at the time we believe this sample was first found or was being used, these were ODE. So this one, there's already a great write-up by Sar Amar, which is an integer overflow in IO mobile frame buffer. And this one is what this talk is about. So when this app was first given to me, and I threw all of these different frameworks in IDA, there are 6 exploits here, and 5 of them all follow a very common, similar structure where they are clearly exploiting kernel memory corruption bugs and all go through the same set of steps to defeat all of the mitigations that Linus was talking about earlier. But one of them does not look like the others at all. And it also has some other kind of interesting and very helpful aspects. So something which you may or may not expect, depending on how many in the wild exploits you've seen. It's full of printf statements telling you what it's about to do. So for example here, failed to prepare fake vtable at some address. But we can learn multiple things from this error message, or from this logging message. And the most interesting when I was first looking at this happens extremely early in the exploit flow. In fact, so early that something very different is going on in this exploit. Because as you saw the extent that Linus had to go to earlier in his Fugu talk to get to the point where he could get PC control in EL1, in the kernel. There were so many steps, yet within probably a dozen lines of code, they already have succeeded or failed to prepare a kernel vtable. This just doesn't make sense. The next sort of cryptic message, they say, waiting for read-write primitives. And you think, well, okay, there have been lots and lots of race condition vulnerabilities in XNU. Maybe there's a race condition, but the code has not got the structure indicating that it would be exploiting a race condition bug. So what's going on? And the last message is the one that gives us the clue as to the path we have to follow, which is unexpected data read from DCP. And yeah, this is the hint that there's something much more interesting going on here. So what is the DCP? The DCP is the display coprocessor. So introduced with the M1 Max and the iPhone 12 and 13. I'm subtly looking at the Apple people in the audience to make sure I get the versions correct. It's an ultra low-level bitmap coprocessor. So it sits in between your processor and the display panel and is doing sort of the last level stuff before your frame buffer hits the display. So for example, on a mobile device, it's talking MIPI, the protocol which the panel expects, or on your MacBook, it's doing the DisplayPort stuff. It's doing tons and tons of low-level processing on a separate piece of silicon. In fact, we can make that a bit more visual. So I put this in a blog post, and then someone told me that the area I very confidently highlighted as the display coprocessor is not the display coprocessor. But anyway, I'm happy for someone from Apple to come up and tell me exactly where it is. But for the purposes of this talk, it is there. So in the sort of 90s, 2000s, when you were building your computer that was this big, you could see these different coprocessors, and you could see the buses that interconnect them. But now, these things have all been compacted right down so that this is all happening on one integrated circuit, on one system on a chip. So what is actually running on here? Well, we can actually get the firmware for this coprocessor. It's called DCP in the firmware. That's how you know this is the name. So how you know it's the right binary. And we can see it's like 3.7 megabytes. And if we run OTool, like it's a Maho binary. Actually, there's a little header you have to remove, but it's just this is a 64-bit ARM 64 Maho binary. So what is actually in here? So at this point, I should point out the display coprocessor is not doing tons of stuff that wasn't happening before. So lots of the functionality is functionality that previously lived in this kernel driver, which was running in the kernel, called IO mobile frame buffer. all of these things like the DisplayPort link training, the MIPI display panel negotiation, all of this stuff had to happen before. It happened in the kernel, and now for reasons which make total engineering sense, it's been moved to a coprocessor, right? It can happen on a lower performance core, more energy efficient. Makes total sense. Of course, the interesting question is, well, how do you do that? How do you take all of this functionality and move it to this coprocessor? And so here I'm going to reveal some pretty secret Apple internal development secrets for how you would port a huge driver to a coprocessor. First, you would highlight the code you want to port across. You use this key combination to move it onto your coprocessor. And this is really the case. So they've taken a huge chunk of this existing IOKit C++ driver and moved it into this brand new world of RTKit. So RTKit is Apple's real-time operating system. I've written here, it's incredibly poorly documented, and there's no public reverse engineering of it. I've already managed to find 2 people in the audience who told me that they've spent incredibly long time reversing this. So if you also have, come talk to me afterwards. I've got lots of questions. But yes, there was lots and lots and lots of reversing that I had to do for this that I'm going to skip over, but you can see the companion blog post if you want to know all of that pain. But effectively, it's custom C++ real-time operating system. And for the purposes of this talk, the things which are most interesting is that unlike those bigger cores that we saw earlier on the M1 and the A14, this one, an RTKit, has no pointer authentication. It has no address space layout randomization. It has predictable heap addresses. And so you're maybe starting to see how the dots are going to connect, that this exploit, which looked like it really didn't have to do enough to defeat all these mitigations, didn't have to do enough to defeat all these mitigations. And if I were feeling particularly mean, some of you will get this reference, but I should probably move on past that. So obviously, there's a little bit more to it than simply all the mitigations are broken, we can trivially compromise this thing. So, but to understand exactly how it works, we need to look at how this communication channel out to this coprocessor works. And for this, you need to know that they chose this boundary of code to move is extremely broad. So really, it's split at the external method level, which is where you, from user space, would interact previously with IO mobile frame buffer. Now, from user space perspective, it looks like you're still interacting with IO mobile frame buffer, but there's another level going on below it. So IO connect call method is how you would typically interact with a kernel driver. This code would generate a Mach message, kind of serialized message buffer, pass it over into the kernel. There's some code there which deserializes that, and the kernel driver user client would handle it. And typically, it would just go right back up into user space. But that's not what happens anymore. It first gets serialized in user space, sent down to the kernel, deserialized, then reserialized using this thing called DCP link, RPC, which will take literally the arguments you passed in user space, serialize them again, and push those over to the display coprocessor. They then get processed here and proxied back up. So we can look at that again with this model just to emphasize the fact that this is happening somewhere else, maybe or maybe not exactly there. So previously it was happening here. So over here, these, where's my mouse? These 4 areas over here are the higher performance cores with the speculative execution bugs. These are the lower performance energy efficient cores with fewer speculative execution bugs. And so previously, this would all happen in there. All right, that's a very high level way of looking at it. But there are at least two different privilege levels on those CPUs. And you're just flipping between those. Whereas now what's happening is you're flipping between those and then hopping over there. But again, that's not quite right? You're really flipping over here, coming into the system cache, maybe out to the DDR controller, back in and back up there. And that's super important to dive into in a little bit more detail to see why there is slightly more going on to why this vulnerability actually works. So I drew this arrow between the display coprocessor and the DDR controller, but this is not actually really fair. The display coprocessor doesn't have direct physical memory access. There is actually something called, in Apple parlance, a DART, which I had to write down what it means, Device Address Resolution Table, which for those from an Intel background is like an IOMMU. The ARM term would be SMMU. So I'll try and do what is an IOMMU in 30 seconds. This is your view of physical memory. This is the real physical memory chips inside your device. And you might have in your user space task, in your process, a view onto some subset of that physical memory, which can be disjoint. So you might have this virtual address mapping to this physical one, like this. And this is implemented in hardware by a memory management unit, MMU, which uses data structures also stored in some other place in physical memory. Well, there is an analogous thing which is also providing a translation for device physical memory, going the other way. So that a device would use an SMMU in ARM parlance, DART in Apple world, to also perform a similar translation such that it can also not necessarily have to have everything in physical, everything doesn't have to be physically contiguous, but the device can see, from the device's perspective, addresses can appear physically contiguous, even if they're perhaps not physically contiguous. And on some platforms, some vendors also use this as a security boundary. And Apple are generally pretty good at also using this ability to restrict or control devices' views of physical memory as a security boundary. Plenty of Android phones also have this technology, but don't actually use it as a security boundary. And the devices themselves are able to control their own SMMUs. But in Apple's case, this is a security boundary. So I gave my extremely hand-wavy explanation earlier of, well, they just like copy-pasted the driver code and moved it to the coprocessor. But obviously, that's not going to work. So above it, they have RTKit providing the operating system sort of scheduling, message box communication mechanisms. But they also need, well, it's also a kind of major engineering challenge to just make the code continue to function. So this code originally expected to run in EL1 in the context of the kernel. So that's what the developers had in mind when they wrote this code. Whereas now, it's got to work in a completely different context, where, as we've seen, it can't even access physical memory in the same way it was able to before. So how do you solve that? Well, to see that, we need to look in slightly more detail at exactly how that communication channel works. So when you make your external method call, it comes down into the kernel and then onto the DCP. So there are these IOKit proxy RPCs, which come right from the top down to the bottom. But then there's also a separate family of RPCs which come up just one hop, which enable the DCP to make requests to the kernel. And these are extremely permissive, at least when this sample was found. These effectively mean that the display coprocessor can just request completely arbitrary mappings to be put into its SMMU table here, which effectively means that the security properties of the DART, in Apple's case, are not actually enforced once you have code execution on the display coprocessor. And this is exactly what this in the wild exploit was doing. It was building fake objects on the display coprocessor that themselves would make these kernel helper RPCs from the display coprocessor up to the kernel and back to the coprocessor to map arbitrary kernel memory such that from user space, they could interact with the DCP and simply read and write kernel memory. Pretty impressive. So, not got much time left, but we'll quickly look at what the actual vulnerability was. the DCP and I/O mobile frame buffer have an enormous amount of functionality. And one of the myriad of things that they do is this thing called uniformity compensation. When the display panel comes from the factory, it is not perfect. For example, there might be brightness discontinuities or color inconsistencies. So it's sort of, these inconsistencies are measured, and they make a data structure, like a 2D array, like 2D array with a size, showing where the inconsistencies are in the panel, such that the DCP can communicate this to the panel and it can correct for it. And I'm not going to go into any details about the bug, but yes, it's C++, there's memory corruption, and just if you write your code in C++, this is what's going to happen. I'm not going to cover it in any detail, but go into the companion blog post, and it covers exactly how they managed to turn this around. The key takeaway is that this thing doesn't necessarily have new bugs. It just has way, way easier exploits. Apple have taken the totally defensible position that fixing all the bugs is too hard. And this is fine. And they've instead said, we're going to focus on mitigations. But the problem then is that if your mitigations also regress, you're going to have a bad time. And so I have to have a mandatory picture of an iceberg on the last slide. So today we spoke about the display coprocessor. It won't surprise you to learn this is not the only coprocessor. What about the always-on processor? Or the U1 ultra-wideband? Or the Apple video decoder? Or the Apple video encoder? Or the secure enclave processor? Or the Apple GPU? Or the neural engine? Or the Bluetooth low energy processor? Or the Wi-Fi processor? Or the baseband? So yeah, plenty more to do. Thank you. And yeah, happy to answer any questions. Otherwise, just come find me. I'll be here until tomorrow. There is a question at the back. So RTKit runs, they have lots and lots and lots of different versions of RTKit that run everywhere. Like it's the operating system that runs on your right headphone, and it also runs on your left headphone. It runs absolutely everywhere. And yeah, lots of those coprocessors run it. Exactly which ones, I'm not sure. But there are people here who know. They may or may not identify themselves to you. Oh, yes?
If you have a look at the malicious activities that you're executing after you can exploit?
Absolutely, and if you look at the tag, so Google's threat analysis group blog post, they go into much more detail about what they were actually doing with the implant.
I don't think so. At least I read it yesterday to prepare for my talk, but I didn't find anything there. So I read your first report of that implant in 2019, and I would have hoped that there's another analysis for that as well.
Okay. Yeah.
Do you have any sense of how business of all power forward? Do you have any sense of the difficulties that Apple brings modern innovation and once the GCP but developable
I don't know if anyone has, certainly I don't know, I'm pretty sure Apple haven't published any of what the performance impact in terms of, operations per second or also like energy cost is to doing things like pointer authentication. I have no idea, but I imagine it would be non-trivial. And I think part of the advantage of moving these things to the lower power cores is specifically to reduce, to make the thing more performant. But obviously there is a trade-off there. Sure. Cool. Thank you, everyone.